Thank you very much for tuning in and watching. I would also like to thank the American Institute of Ultrasound and Medicine for creating a venue for research presentations like this to take place despite the cancellation of the 2020 annual meeting in New York in these unprecedented times. Thank you very much. My name is Mike Blaivas, and I am presenting an abstract entitled, "Are All Deep Learning Architectures Alike for Point-of-Care Ultrasound? Evidence from Cardiac Image Classification Models Suggests Otherwise." I do have 3 potential conflicts to disclose. None of these companies were in any way involved with the project, nor aware of it. I have one co-author to thank, Mrs. Laura Blaivas. Little is known about the optimal deep learning approaches for point-of-care ultrasound. There have been fairly limited publications on the topic, and only now are we seeing some commercial development in that area after more advanced applications in traditional radiology and cardiology settings have been explored. Most applications are developed for facial recognition, surveillance, autonomous car operations, and sport video analysis. And this is really the background of most deep learning video and image analysis. And it was simply brought over recently to medical applications. We compared 6 popular deep learning architectures for point-of-care cardiac image classification in order to determine if there is an optimum deep learning architecture for future deep learning algorithm development in POCUS. We trained 6 convolutional neural networks with a range of complexity and age. They included names like AlexNet, VGG16, VGG19, ResNet50, DenseNet 201, and Inception v4. These are all household names to deep learning algorithm developers. Each CNN trained on 5 typical point-of-care ultrasound cardiac views. We extracted images from 225 publicly available point-of-care ultrasound cardiac videos that were all de-identified of any patient information. This yielded 750,018 individual images which were extracted. 90% of these were used for model training. Another 10%, which was randomly selected, was used for cross-validation during the training. Training times for each architecture or algorithm and accuracy achieved were tracked. A real-world test was then performed for each algorithm on 125 completely new cardiac images, which the algorithms had not seen before. Descriptive statistics, Pearson's R and kappa values were calculated for each CNN. Accuracy for the 6 CNNs studied ranged from 96% to 85.6% correct. VGG16, one of the oldest and simplest CNNs, performed best with a 96% correctly classified portion when compared to the other CNNs which are listed in the table. The VGG16 architecture took 232 minutes to train on our computer. It achieved a Pearson's R of 0.97. The kappa was 0.95, and this yielded a p-value of less than 0.00001. Interestingly, the worst performing CNN was a very much newer one, DenseNet 201. It's also a much deeper and much more complex CNN. It achieved an accuracy of 85.6%, took 429 minutes to train on the same computer with the same images, achieved a Pearson's R of 0.92, a kappa of 0.82, and a p-value of less than 0.0001. The 6 common image classification deep learning algorithms showed considerable variability in accuracy and training time when trained and tested on identical data. This suggests that not all deep learning algorithms perform optimally for point-of-care ultrasound deep learning applications. Contrary to well-established and known accuracies and performance metrics for CNNs, the more modern and deeper algorithms yielded poorer results. Thank you again for listening, and be aware that this article has now been published in the Journal of Ultrasound and Medicine and is available online for review. Please contact me with any questions.